Is our universe truly one of a kind, or have countless others come and gone before it? The James Webb Space Telescope has once again revealed something that defies our current understanding of the cosmos. A recently discovered galaxy suggests we may have been fundamentally wrong about the so-called cosmic dawn. Alongside other puzzling structures uncovered by Webb, this finding is leading more scientists to question the traditional Big Bang model. Many now believe the universe may have followed an entirely different path. Among them is British Nobel laureate Roger Penrose, who argues that the cosmos moves through endless cycles of birth and destruction, and he claims to have found tangible evidence supporting this theory. Today, we're diving into the astonishing discoveries made by the James Webb Space Telescope, findings that hint some cosmic objects might even trace back to a universe before our own. Too early, too massive, too mysterious. When the telescope scanned a region of the sky near the Big Dipper, astronomers spotted strange points of light that had been journeying through space for over 13 billion years. These signals came from objects that existed just 500 to 700 million years after the Big Bang. Based on their properties, scientists identified them as early galaxies. But here's the shocking part: these galaxies were already as massive as the Milky Way is today. According to our current cosmological models, that shouldn't be possible. There simply wasn't enough ordinary matter back then to form such colossal structures. These enigmatic giants have since been nicknamed universe breakers, and they're challenging everything we thought we knew about the early universe. The astronomical research community was already facing serious challenges, but that was just the beginning. In the period that followed, the James Webb Space Telescope detected even more galaxies that seemed far too developed, too rich in stars, for their young age, just a few 100 million years after the Big Bang. Webb also confirmed another major inconsistency: the rate at which the universe is expanding doesn't align with our theoretical predictions. This rate, known as the Hubble constant, is calculated to be about 67 kilometers per second per megaparsec on paper. However, when we measure it using observations of supernovae, red giants, gravitational lensing, and variable stars, we get a different result. The Hubble constant has now been measured at 73 kilometers per second per megaparsec, a significant value that, if confirmed by future James Webb observations, would reinforce the striking discrepancy between theory and observation. But how can this be? How can such a dramatic deviation from theoretical predictions be explained? One of the most fascinating hypotheses proposed by researchers suggests that our universe may currently be interacting, or even merging, with other universes. According to this idea, the true cause of cosmic inflation, the period of faster-than-light expansion shortly after the Big Bang, might have been our young universe being absorbed into a much larger, mother, cosmos. To explore this possibility, scientists have developed a mathematical model to examine the potential effects of multiple interacting universes on our own. Their conclusion? Such a scenario would lead to an increase in the observed Hubble constant. The volume of our universe, and its apparent growth, may be influenced by factors that our instruments interpret as cosmic expansion. Remarkably, scientists have now calculated the rate at which such an expansion would occur under this new perspective, and to their surprise, the results align more closely with actual space observations than predictions made by the traditional Standard Model. This discovery, made possible by the James Webb Space Telescope, is challenging our understanding of the early universe. Many experts now openly acknowledge that our current view of the cosmos is incomplete and that crucial elements may still lie beyond our detection. Once again, Webb's latest findings highlight just how much there is still to uncover about the universe. We still have much to learn about the evolution of the cosmos. In science, an assumption is only accepted until it's challenged by a contradictory observation. To truly understand this, we must turn back the clock to the cosmic dawn, a period when the universe's first young stars ignited. These early stars not only illuminated the universe for the first time but also ionized the previously neutral hydrogen. Before this, clouds of interstellar hydrogen acted like a thick fog, scattering and absorbing ultraviolet and other shortwave radiation, plunging the cosmos into darkness. Experts generally believe that the era of reionization began about 300 million years after the Big Bang. Model simulations suggest that the first openings in the hydrogen fog were already forming around that time. However, the regions that were permeable to shortwave radiation were thought to be limited, forming only small, bubble-shaped zones around early galaxies. That's because, at the time, only those areas had young stars capable of ionizing the surrounding gas. At least, that's what we believed, until now. Thanks to JWST's discovery of GSZ 11-1, the James Webb Space Telescope has identified a galaxy that existed just 330 million years after the Big Bang, surprising the scientific community. What's truly remarkable is that this star cluster is emitting an extraordinary amount of shortwave ultraviolet radiation for such an early point in cosmic history. The redshift observed in the spectral signature of excited hydrogen corresponds to what is known as Lyman alpha radiation. However, this finding is deeply puzzling. It contradicts our current understanding of cosmic evolution. According to established models, Lyman alpha radiation could only travel freely after the dense hydrogen clouds in the early universe had been ionized across vast regions, something believed to have occurred much later. Astronomer Joris Wittek from the University of Cambridge, who led the study, described the surprising discovery, saying, "This was completely unexpected. Although we're observing this galaxy as it was just 330 million years after the Big Bang, it clearly shows a strong and well-defined Lyman alpha signal." His colleague and co-author, Kevin Hanine, echoed the sentiment, adding, "We shouldn't have found a galaxy like this at all. And yet, there it is." The spectral data leaves no room for doubt. The galaxy's ultraviolet radiation extended much farther than anyone had previously imagined. Scientists have concluded that the bubble of ionized, and therefore UV-permeable, gas must have stretched over 650,000 light-years in every direction. This, in turn, suggests that cosmic reionization either began significantly earlier than expected or progressed much faster than current models predict. Could this be evidence of a cyclical universe? Perhaps. But the discovery also points to a new understanding. Smaller, less massive early galaxies may have played a much larger role in reionization than we once believed. The exact source of the intense ultraviolet radiation detected from this structure remains a mystery. Scientists suggest that this large bubble of ionized hydrogen may have been formed either by a rare population of extremely hot, luminous primordial stars or by an active black hole at the galaxy's center. But what do these puzzling discoveries really tell us about the universe? As we continue to uncover phenomena that don't align with our current models of cosmic evolution, it raises a deeper question. Could we be fundamentally mistaken about how the universe works? What if the Big Bang wasn't the absolute beginning of everything, but rather a violent transition from one universe to another? If so, that idea would lead us directly to the core belief of physicist Roger Penrose. After all, the British Nobel Prize-winning physicist is convinced that the cosmos is governed by a continual cycle of destruction and rebirth. According to this view, the widely accepted Big Bang was more accurately a big bounce. The universe, he suggests, expands until all matter breaks down and transforms into pure light. And true to the idea that what expands can also contract, this extreme state, where time and space lose all meaning, would eventually trigger a new cosmic explosion, giving rise to a fresh universe. What's even more intriguing is that this theory opens the door to deeper and more thrilling possibilities. Penrose asserts that he has already uncovered solid evidence supporting his cyclical view of the universe. He suggests that objects directly originating from our precursor universe are currently lying dormant in the far reaches of space. But what does this really mean? Penrose and his team have detected a remarkable signal in the cosmic microwave background, CMB, which is radiation left over from about 380,000 years after the Big Bang and continues to permeate the universe today. It is within this radiation that Penrose and his colleagues identified circular patterns in the data from the Planck and WMAP satellites.